Welcome all. In the first session of plastic deformation of metals, we discussed process of slip, then process of slip by dislocation moment. Now, in this topic, we will discuss characteristics of dislocations, strain field interaction of dislocations, slip systems, slip in single crystal, then plastic deformation of polycrystalline materials, and finally we will discuss summary. Several characteristics of dislocations are important with regard to the mechanical properties of metals. These include strain fields that exist around dislocations, which are influential in determining the mobility of the dislocations as well as their ability to multiply. When metals are plastically deformed, some fraction of the deformation energy, approximately 5%, is retained internally. The remainder is dissipated as heat. The major portion of this stored energy is as strain energy associated with dislocations. Consider the edge dislocation which is shown in this particular figure. As already mentioned, some atomic lattice distortion exists around the dislocation line because of the presence of the extra half plane of atom. As a consequence, there are regions in which compression, tensile and shear lattice strains are imposed on the neighboring atoms. For example, atoms immediately above and adjacent to the dislocation line are squeezed together. As a result, these atoms may be thought as of experiencing a compressive type stress field related to the atoms positioned in the perfect crystal and far away from the dislocation line. So directly below the half plane, the effect is just the opposite. Lattice atom sustain an imposed tensile strain, which is shown in this particular figure. As you can see, shear strain also exists in the vicinity of the edge dislocation line. Strain field interactions. Strain field interaction of dislocations. The strain fields surrounding dislocations in close proximity to one another may interact such that forces are imposed on each dislocation by the combined interaction of all its neighboring dislocations. For example, consider two edge dislocations that have same sign. So C means compression and T means tensile. Consider here two dislocations on the same plane of the same sign, so you can see the repulsive forces are observed. Whereas in this particular figure, two dislocations of the opposite sign, they attract with each other, and when they attract with each other, they combine and they form perfect crystal. So means dislocation annihilation occurs. So means the two extra half plane of atoms combines together and it forms one plane. So dislocation annihilation starts. So dislocation annihilation means dislocation density decreases. Slip systems. Dislocations do not move with the same degree of ease in all crystallographic planes of atoms, and in all crystallographic directions typically there is a preferred plane, and that plane there are specific directions along which dislocation motion occurs. So this plane is called the slip plane. It follows that the direction of movement is called slip direction. So this combination of the slip plane and the slip direction is called slip systems. The slip system depends on the crystal structure of the metal and is such that the atomic distortion that accompanies the motion of a dislocation. For a particular crystal structure, the slip plane is the plane that has the dense atomic packing, that is, it has the greatest planar density. The slip direction corresponds to the direction in this plane that is most closely packed with the atoms, that is, has the highest linear density. So let us discuss the slip systems in more detail by considering the example of face-centered cubic structure. In case of face-centered cubic structure, Family of 111 plane are the highest dense packed planes, whereas family of 110 are the close packed directions. So combination of family of 111 and family of 110 direction constitutes slip system in case of face-centered cubic system, face-centered cubic structure. Remember that these three directions, if you find out the Miller indices of these three directions, you will get the Miller indices in the combination of bar 110 or 1 bar 10, but you will not get 110, or you will not get the direction of 110 combination. So means 110 is a not the 110 is not present, is does not lie over the slip plane. So that's why you cannot count in the calculation of slip systems. If you find out the Miller indices, you will get the Miller indices in the combination of three combinations. You can see three different slip directions exist for the one particular plane 111. So thus several slip systems may exist for a particular crystal structure. The number of independent slip systems represent the different possible combinations of slip planes and directions. In case of face-centered cubic, there are 12 slip systems, 4 unique family of 111 planes within each plane, and 3 independent family of 110 directions. A slip plane and slip direction that lies on it together constitute a slip systems. Remember that the direction has to lie within the slip plane, then only we can consider in the calculation of number of slip systems. If the direction doesn't lie over the slip plane, it doesn't form slip system. So that's why we will not consider 110 as a part of slip systems in case of face-centered cubic structure, because in this particular scenario the Miller indices of three directions, these three slip directions are not 110. The possible slip systems for BCC and HCP crystal structure are shown in this particular table. There is no unique slip plane for these two crystal structures. These are possible slip planes. For each of these structures, slip is possible on more than one family of planes. For example, family of 110, family of 211 and family of 321 for body-centered cubic structures. For metals having these two crystal structures, some slip systems are often operate only at elevated temperatures. Remember that only at elevated temperature some of the slip systems will operate, means that these two crystal structures, the metals having these two crystal structure, they have low ductility at room temperature. Metals with face-centered cubic structure or body-centered cubic structure have relatively large number of slip systems, at least 12. You can see these metals are quite ductile because extensive plastic deformation is normally possible among the various systems. So slip systems are very important in plastic deformation process. High number of slip systems means more dislocation movement, and more dislocation movement means more plastic deformation. Conversely, HCP having few active slip systems at room temperature, so that's why they are normally quite brittle. Slip in single crystals. As mentioned previously, edge, screw and mixed dislocations move in response to shear stresses applied along a slip plane and in a slip direction. Slip always occurs on a particular set of crystallographic planes known as slip planes. Slip always takes place along a consistent set of direction within these planes, and these are called slip directions. The combination of slip plane and slip direction together makes up a slip system. In order for the dislocation to move in its slip system, a shear force acting in the slip direction must be produced by the applied force. The slip direction must lie in the slip plane. Slip occurs by dislocation motion. To move dislocation, a certain stress must be applied to overcome the resistance to dislocation motion. For an applied stress, pure tensile or compression, shear component always exists but parallel or perpendicular alignment to the stress direction. So these are generally termed as resolved shear stresses, and their magnitude depends not only on the applied stress but also on the orientation of slip plane and direction within that plane. Slip occurs when the shear stress acting in the slip direction on the slip plane reaches some critical value, and this critical shear stress is related to the stress required to move dislocation across the slip plane. In order to understand what is the force required to initiate slip in case of single crystals, let us discuss or let us assume or consider this figure. So let this phi represent the angle between normal to the slip plane and the applied stress, and lambda be the angle between the slip direction and the applied stress. So it can be then shown that for resolved shear stress, so tau r can be written out as sigma equals to cos phi cos lambda. A metal single crystal has a number of different slip systems that are capable of operating. The resolved shear stress normally differs, the magnitude of this resolved shear stress differs for each slip system because it depends on the angle of phi and lambda. Because for each slip system, so this is the one example, so this is one slip systems. So for different slip systems or number of slip systems, so magnitude of this resolved shear is different since the angle phi and lambda for each slip system is different. However, slip will start on most favorably, that is has the largest shear stress, or slip will start over the slip plane which has largest value of shear stress. So we can write tau r maximum equals to sigma cos phi cos lambda, that is maximum. In response to an applied stress, tensile or compression, slip in single crystal commences on the most favorably oriented slip systems. When the resolved shear stress reaches some critical value, termed critical resolved shear stress tau RSS, it represents the minimum shear stress required to initiate slip and is property of the material that determines when yielding occurs. The single crystal plastically deforms or yields when tau r maximum equals to tau RSS, and the magnitude of the applied stress required to initiate yielding is nothing but sigma y. So you can rearrange the term and we will write this equation. So sigma y equals to tau r divided by tau CRSS divided by cos phi cos lambda, that is maximum. The minimum stress necessary to introduce yielding occurs when a single crystal is oriented such that angle between phi and lambda equals to 45. Under this condition, tau RSS is nothing but maximum value. So tau RSS equals to 1/2 sigma y. It is observed experimentally that a single crystal will slip when the resolved shear stress on the slip plane reaches a critical value, and this behavior is known as Schmidt's law, and this factor cos phi cos lambda is called as Schmidt's factor. For single crystal specimen that is stressed in tension, you can see single crystal specimen which is stressed in tension is shown in this particular figure. When a single crystal is deformed under a tensile stress, it is observed that plastic deformation occurs by slip on well-defined parallel crystal planes. Sections of the crystal slides related to one another. Each step, you can see here, each step results from the movement of large number of dislocations along the same slip plane. On the surface of polished single crystal specimen, these steps appear as slip lines. So this is a single crystal zinc specimen that has been plastically deformed to the degree that slip markings are easily seen over the surface of the single crystal zinc sample. With continued extension of single crystal, both the number of slip lines and slip step width increases. As we have already seen, for phi and lambda equals to 45 degree, tau r SS is maximum. But when phi and lambda equals to 90 degree, phi and lambda for 45 degree, tau r SS is maximum. But when you substitute lambda and phi value equals to 90, in that case critical shear stress is 0. And for these extreme conditions, the crystal typically fractures rather than deforms plastically. So this is one of the reasons why SCP crystal structures are brittle in nature. The importance of small amount of impurities in increasing the critical resolved shear stress is shown in this particular table. As you can see, for Ag, for purity, crystal structure is face centered cubic structure. Purity is 99.99. In that case, critical resolved stress is 0.48. As the impurity increases from 97 to 93, the critical resolved stress value has also increased. Similarly, you can see for titanium. So means the importance of impurities over the critical resolved stress is very important. In solid solutions where the solute atoms differ considerably in size from the solvent atoms, a greater increase in critical resolved shear stress is observed, and that we will study at the time of strengthening mechanisms. Plastic deformation of polycrystalline materials. Deformation and slip in polycrystalline material is somewhat more complex because of the random crystallographic orientations of the numerous grains. The direction of slip varies from one grain to another. For each dislocation motion occurs along the slip system that has most favorable orientation as defined earlier. So this figure shows polycrystalline sample of a copper that has been plastically deformed. So before deformation, the surface was polished. Slip lines are visible. You can see slip lines are visible. And it appears that two slip systems operated for most of the grains. As it is evidence, as you can see, two slip systems are visible here due to two sets of parallel yet intersecting set of lines. So within the grain, two slip systems are operating because one slip lines are parallel to each other and second slip lines are again they are parallel to each other, but both the slip lines are intersecting with each other, means more than one slip system is active in this particular grain. The manner in which grains distort as a result of gross deformation is indicated in this particular figure. Before deformation, the grains are equiaxed, or they have the same dimension in all the directions, means they are equiaxed grains. For this particular deformation, the grains become elongated when you apply the load uniaxially. So grains elongate along the direction in which the specimen was extended. So polycrystalline metals are strong than the single crystals, which means that greater stresses are required to initiate slip and to start yielding. So even though a single grain may be favorably oriented with applied stress for slip, it cannot deform until the adjacent and less favorably oriented grains are capable of slip. So this requires a high applied stress level in case of polycrystalline material. And also in case of polycrystalline material, large number of grain boundary is present, and these grain boundary are also obstacles for the dislocation motion, and due to that greater forces are required to start the plastic deformation. So finally we will discuss the summary of today's topic. The motion of dislocation in response to an externally applied shear stress is termed as slip. Slip occurs on specific crystallographic planes and within these planes only in certain directions. A slip system represents a slip plane, slip direction, combination of slip plane and slip direction. Operatable slip systems depend on the crystal structure of the material. The slip plane is that plane that has dense atomic packing, and the slip direction is the direction within this plane that is most closely packed with atoms. The resolved shear stress is the shear stress resulting from an applied tensile stress that is resolved onto a plane that is neither parallel nor perpendicular to the stress direction. Its value is dependent on the applied stress and orientations of plane and direction. Critical resolved shear stress is the minimum resolved stress required to initiate dislocation motion or slip and depends on yield strength and orientation of slip components, that is cos phi, cos lambda. For a single crystal that is pulled in tension, small steps form on the surface that are parallel and loop around the circumference of the specimen. So that we have seen in case of single crystal zinc sample. For polycrystalline metals, slip occurs within each grain along the slip systems that are most favorably oriented with the applied stress. Furthermore, during deformation, grains change shape and extend in those directions in which there is a gross plastic deformation. So polycrystalline materials are more stronger than their single crystals because more obstacles are present in case of polycrystalline material for the slip to occur.